Hello, everyone. I am Kalyan Veeramachineni. I'm a principal research scientist in the MIT's new Data Systems and Society Institute. I run a lab there called Data to AI, and we focus a lot on building artificial intelligent applications from data. And I'm going to present today one such application that we built a couple of years ago, and I'm going to tell you in the energy sector, and I'm going to tell you how we approached that problem, what it enabled, and how it had changed things, and how we tested and validated it, that particular approach. And then I'll give you a little bit of a preview of what we are, in what direction. Oh, sorry. In what direction we are headed towards, and some challenges that we faced while we were building this. So there's a lot of collaborators on this project. Tisha was a primary student who worked on this project. She was my student. She then went ahead and started the company on this concept, and I'll share that information as well. So the problem was that we wanted to figure out how we can use machine learning to estimate what sort of wind resource will be at a new test location. So before you set up a wind farm or a wind turbine, what you usually do is you set up an equipment there to measure the wind speed for a short duration of time, and then you try to correlate that with sites that have wind measurements for a longer duration historically, and then you try to see how much does that correlation match up for that duration of time, and there is an overlap, and you try to project how much wind will be there in that particular site over a longer duration. And if future is going to be the way it has been in the past, we will have similar amount of wind resource or wind speeds in that location, the test location, and we can estimate the energy that we may produce if we were to put a wind farm. So that's basically that's the problem. We started thinking about this problem around 2011, 2012 timeframe, and we looked at whatever the approaches that wind industry was using to solve this particular problem, and we found they were using a very simplistic approach. They will take the nearest airport to that test location. They will correlate the data, and then they will try to use a very linear model, a very simplistic model, where they'll take the ratio between the wind speeds here for that duration and the wind speeds there, and use that ratio value to actually adjust the wind speeds there to estimate here. So it was a very simplistic model. So how can AI or how can machine learning help improve that? So we just jumped into the project just to do it. We didn't know if it would improve it because this is an industry standard, the linear model that has been used for a long time, and wind energy is a complex field, and I'm certainly not an expert in the wind energy field. So as I mentioned, it's also popularly called measure, correlate, predict. And measure comes from when you try to measure the wind speed for a short duration of time at a test location. Correlate comes from you correlate that wind speed to all the other locations nearby you have measurements for past 20 years. And once you correlate that, you try to predict what would have been the energy here, or what would have been the speed here at this particular location. This is just a way to tell you that there's like a series of steps that we followed. We collect the measurements. We model what we call a joint distribution. So what was different between what we tried versus what was the standard in the wind industry at that time is that we were trying to model a joint distribution. A joint distribution also factors in the sort of covariance between variables, and so it doesn't assume independence. The variables here being the measurements at the test site as well as the long-term site. Once we have that joint model, we can now make predictions given the measurements at the long-term site, what would be the test site measurement. So that's a very simplistic probabilistic model, very used a lot in machine learning for other problems. So we tried to see if we can use this particular method in this domain. There was one particular innovation that we did, which was called the Copula Functions. That was also new in the machine learning sphere. So that was not the way you model these joint distributions, was using sort of a normal or a Gaussian or a bell curve. Copulas allow you to actually model some nonlinear correlations as well as long-tail distributions. So that's just one innovation in the machine learning community itself that we tried to bring or add on to our modeling technique. What we did first was we took the test site. For test site, we took data from Museum of Science locally here in Boston. And we took that test site, and there's 5 anemometers. Those are the measuring equipments that measure the wind speed and direction from the rooftop of Museum of Science. They had collected data for 2 years, and they were good. They were very generous enough to give us that data to test our algorithms on. And to correlate with long-term sites, we scanned through all the databases that were available publicly and got all the data from all the airports in Massachusetts. So there was 14 airports that we collected the data and collated. So one task was to actually map up the timestamps, and that's what we call in data science or AI the curating and cleaning part of it. We had to map up the timestamps, and we had to bring them together and merge them. So once we had that, we applied our model, and we started testing of how our model, if given a short amount of data, how well would it predict and how well we did estimate the wind speeds at the test site. And we have the ground truth because we had collected data for 2 years, so we had ground truth to actually test how well it does. This is just a plot of, on y-axis is a plot of how good our predictions were. On x-axis is for each directional bin, so we actually bin the data for each sort of a sector. There's like 12 sectors, so 30 degrees we bin the data. And then we model for each bin, we build a separate model, and this is the sort of the test of how well we do along different bins. So what you would notice here is that these two are the blue and the blue one especially, the pink and the blue one are the industry standard. That's what was being used before we started using our models. And what you would see is that our models are the black and the red, and you'll see our error rates or the y-axis we are trying to minimize. Our error rates are as low as possible. What is more interesting here is the industry has a standard here. They actually try to collect the data at the test site for 8 months of time, and they have that defined that we have to, for good sort of a measure, correlate, predict sort of approach, we need to have at least 8 months of data. That's what they emphasize. So if you see, actually, once we have 8 months of data at the test site, 8 months of measurements, almost all methods starts to do good. So they are right. They actually need, for their methods, they actually need 8 months worth of data. But this one is actually only 3 months worth of data. So at 3 months worth of data, our method was able to perform better than what their methods were able to perform. So in effect, what this algorithm did was it did not actually improve the accuracy when it comes to 8 months of data. It just shortened the time for the time for which we had to collect the measurements. So that was sort of the innovation, or that was sort of the boost that we were giving using a new algorithm or a new approach, borrowing it from machine learning, adding on a few additional things, and so on and so forth. Once we did that, it still sounded like an academic exercise, and that actually, over years, I have worked on different AI projects and different AI applications, and every time I build it, we publish a paper. We make sure to tell in the paper that we train the algorithm, train the model using the data that is for training, and then we test it on the data that has the algorithm or the model has never seen before, and we publish the papers, and then we go to industry and they say, well, we have to do our own testing. So nobody actually, it doesn't matter how thorough we are in our research paper, how much code we release, how much data we release, how many proofs we write. And that is true for any AI application that I've built so far. Industry wants to do their own testing. So in this case, we went to AWS TruePower, and we asked them if we can test our algorithm on real wind sites that they have. So they gave us 3 data sets, one from each of these states, Maine, Indiana, and Nebraska, from their real wind farms. So at wind farm, they have a Met Tower. They have been collecting wind speeds and directions for a while, and they can now give us 6 months worth of data to build our model, and asked us to make predictions for 2 more years beyond those 6 months, and they never gave us the 2 years worth of data. So we don't know what the truth is. So we just trained our model, and we gave it back to them. The way we trained our model is, again, we took We took the nearest sites from the airports and the data from the airports and so on and so forth, built our model, made the predictions, handed them back, those predictions, to get evaluated on the data that we didn't have any access to. Again, our sort of, we saw the similar pattern. If we have actually, the linear regression model is what the industry standard is, and we saw the similar pattern. In some of the bins it doesn't do well, whereas the Copula model across the bins it does do well. What was more interesting is it took us a lot of time to actually pull the data together from different airports and correlate it and build these models. It took us roughly 6 months to do this process, 6 to 8 months to do this process. And when we gave them back the predictions 6 to 8 months later, from AWS TruePower, the person checked our predictions and said, yeah, you did, what we have in our in-house algorithm, you did very similarly well, and you did perhaps 4.5% better. So that's great, but it's not that impactful. I think after 2-3 days and 2-3 iterations of going back and forth in the email, he and I, when we were going through the conversation, he realized, oh, wait a minute, I only gave you 6 months worth of data, not 8 months worth of data. I said, yes, you only gave me 6 months. So we forgot the fact that, he forgot because we took so long to build the model and so on and so forth, he forgot that he had only given us 6 months worth of data. So that actually in turn means, oh, so you are able to make these predictions with just 6 months worth of data. Then it meant something to them. After that, we spun out as a company. My student went ahead, Tisha went ahead and spun out a company. They had 2 transitions. They changed the name. They actually moved into the financial sector where we try to use this algorithm to support banks rather than actually supporting the BIN consultants. I was very loosely sort of associated with the company, but they went ahead and built that company and got acquired last year. So what are the things that we learned where it can help in all the AI applications that I've been building across different domains? It can transform an existing practice. So it can, but what I mean by that is you already have a data source. There's a well-established problem like measure, correlate, predict in this case. We can transform it, we can disrupt it, but it requires a lot of patience and a lot of testing and validation, because now you're going into a domain and you're trying to tell them that we will do it differently and we'll do better than what you have been doing for a while. What that means is that we would have to work with them to be able to test it, validate it the way they will feel comfortable, establish trust in the models, explain the models, and so on and so forth. So it requires a lot of back and forth between the domain experts and us. We can bring new applications to life, and that's actually an easier task, because these are the applications that are coming from data sources that were never collected before. These are the new data sources that are coming, and then we can actually build the models from those and make predictions or do things with that data that actually has no pre-existing sort of a model or a problem defined. We are now, since 2013 onwards, since this project actually finished and then we moved it on to the commercial space, we have been building systems, a lot of systems to make these processes efficient, not just the processes, the processes of resource assessment, but also the process of how we build AI systems and so on and so forth. All the time, this is my experience, we are never ever able to remove domain experts. We are always able to have to augment the domain experts. I don't think even in that case, our algorithm made it in, but people are just using it as another suggestion or as another input for analysis. My group works on, as I mentioned, removing the bottlenecks in building and deploying such AI systems. Data is always the key. Data always gets sort of nowadays undermined when AI is talked about, but no AI system has ever been built without data, so that's something to keep in mind. The last but not the least, in 2016, DARPA announced, so as I said, we took us 6 to 8 months to build that model. Even though we used all kinds of existing technology, we actually didn't invent anything brand new in machine learning or statistics that powers these models. But it took us 6 to 8 months to collate the data, clean the data, curate the data, build the model, test the model, and so on and so forth. DARPA announced how can we shorten that time and how can we enable people who are not like Kalyan to be able to do that process. So that's a program. We are part of that program that is to automate this whole process of building AI systems, enabling domain experts to do that. So in this case, True Power or other folks in energy sector can directly do what we tried to do. So MIT and Feature Labs together are part of that program. We have delivered our first system last week that works on a number of data sets and tries to build models automatically, data sets that we have never seen, neither our systemers see. So,
all right. Let's take maybe 2 questions. So is this on? Yeah. So you're going to catch that, and then talk into the mic.
I like this. I should bring this to IEEE. 2 questions real quick. 2 degrees and 358 degrees are close. But when you statistically evaluate them, obviously you address that. So I guess one question is, are you familiar with circular statistics and works of Professor Rao, which is specific to migrating birds and stuff like that? It's actually kind of interesting.
Okay.
So you know what? That's the question. We're good.
all right. I'm not aware of that, but I will take a look.
You probably know that.
Yeah.
Okay, I'm going to throw it at you.
No, don't.
All right. So let's make the next question a question.
So 2 questions, actual questions. So question 1 is 3 months. I would imagine there's tremendous bias in selection, seasonal variation and the like, but I'm curious if that's wrong intuition. Second question is, what are the financial implications of this? Is there any CapEx implication or OpEx implication? And then, what have you looked at the business case?
Thanks. I'll address the first question is asked a lot because 3 months doesn't capture all the seasonal variations. So one is, which 3 months did we pick matters a lot in which state. So we actually when we were training the model, we tried to move that 3 months around a little bit to figure out what 3 months will get us the maximum accuracy, not on the test data, but within the training data set, we can self-evaluate. And the second thing is we can apply some corrections to once we have the model, we can actually apply corrections for annual or seasonal variations. So from year to year also there are some variations. So we actually can apply correction, and that's just a multiplier at the end. So we get some parameters for the distributions, and we have some multipliers to make that correction. So there was one more thing that we did in addition to that. The second question is the business implications. That's a very good question. Once we took it out into the commercial space, I was not very closely associated with the startup that my student founded, but I heard a lot of things about taking this to actually through the financial model required a lot of additional work too. And in the end, they ended up actually creating a tool, as I understood it, for the banks. So originally I was targeting how can we improve wind resource assessment for the wind consultants, and how can we do better than what they have done or shorten the time that they have done. What they found was that a better sort of end user for this sort of a software is the banks, because they want a third-party assessment and their own assessment for wind resource, because these consultants go and propose that this is how much wind will be produced at the site and so on and so forth. So there's the translation of what business model we should go after, what problem we should tackle, and that translation oftentimes also takes some time and understanding of the domain.
All right, let's thank Kalyan. Thank you very much.